All right, now in section 1.4, we're going to talk about uh, some really fundamental stuff. There are three big topics in 1.4, so we're going to spend 3 days on this. The first idea is one-sided limit. So we talked about this briefly in pre-calculus, but let's talk about it again. So if we look at this graph here, what is the function, oh, I'm sorry, where is the function going to as x approaches 2, so that means limit, right? X approaching 2, but this time it's from the left. So where is the function going to, being y? So where is y going to when x is going to 2 from the left? So x equals 2 is here. Looking at the function from the left, we see that this function is going down to -2. So this is -2. All right, second question. Where is the function going to as x approaches 2 from the right? So again, this is x equals 2. We're looking at the function going to x equals 2 from the right. So this is the right hand side of the function, and then this function as it's going to 2, the y value is going to 0. Okay, now let's look at the last question. Where is the function going to as x approaches 2? Where is the function going to as approaches 2? So remember, this really means limit as x goes to 2 of the function. So what is that? We already learned it from the previous two sections that in this case, both sides of x equals 2 do not go to the same y value. Therefore, does not exist. Now, how do we go back to the two questions before and say write a limit notation for that information instead of writing it as words? Where is the function going to as x approaches 2 from the left? Can we write a limit statement that represents the same thing? Yes, we can. Limit as x approaches 2 from the left. From the left, remember, means coming from the more negative side. So then we put a small negative as a subscript of 2, and that tells me it's coming from the left of the function, and that we said was -2. And then same thing for the second one. The function, so the limit as x approaches 2 from the right. From the right means numbers that are more positive. So more positive of the function, and that is going to 0. Okay, so this is the idea of left-handed limit that is coming from the left-hand side, and right-handed limit that is coming from the right-hand side. So what we would say is limit as x approaches c from the negative side or from the left of the function, and let's say it has a limit. So this is from the left-hand side, and then limit as x goes to c from the positive side or the right-hand side of some function, and let's just say it's some limit. And then this is kind of the most important thing that we can learn about limit in this chapter, or one of the most important things. So this has to do with proof. So in calculus, you're going to have quite a bit of proofs to show that you can. So when you arrive at a conclusion, you have enough evidence to back your claim up. So this is one of the things that you have to remember, because you're going to use this as part of your proof. So how do you prove that a limit actually exists? Well, you cannot tell them verbally or even written, oh, the left-hand side and the right-hand side are going to the same number. That is not a calculus way of proving. You need to write it in some kind of calculus notation. Therefore, you would say this: the limit of f of x as x approaches c is L if and only if. If and only if a lot of times in textbooks is written as IFF. So that just means if and only if. So they're saying that if, so the limit of f of x as x approaches c is L if. So let me translate this part into calculus notation. So limit as x goes to c of f of x is L only if what? The left hand side and the right hand side are going to the same y value, right? So then this is only a limit if the left hand side and the right hand side are both going to L, then the limit of that function is also going to L. So if the left hand side goes to L, the right hand side goes to L, which in this case is not, then both sides being they're going to L, then at that x value, it must also go to L. So this is the big proof for limit. If you want to state that the limit for something is a number, you have to first prove that both sides have that number. So this is, again, a very important one. Please do remember. All right, let's go ahead and look at an example. That f of x equal, and this is a piecewise function, x squared if x is less than 1, negative x plus 2 if x is greater than or equal to 1. Find this limit. So when it says find this limit, you have to say, okay, I need to do this the calculus way. To find this the calculus way, that means I cannot draw a graph and say, here it is. I cannot find a table and say, well, therefore it's this number. That all of that is not, I guess, good enough. You can do that to kind of convince yourself, but then you need to write it in the calculus way to convince the reader. So how do you prove that this limit, or what this limit is? You have to check both sides of this x value. So you have to check what is on the left hand side of, where is the left hand side going to? Where is the right hand side going to? If they are equal, then the limit is that number. If they are not equal, then the limit does not exist. All right, let's check. Okay, limit as x goes to 1 from the negative side. So from the negative side, the piecewise function says if left negative side, that is all the numbers less than 1, we use x squared. Therefore, you put 1 inside x squared. Why do you put 1 inside x squared instead of another number that's smaller than 1? You could, but remember, limit is when you're getting close to 1. You're getting close to 1. So then the question is, when you're almost at 1, almost at x equals 1, what would the y value be? So you don't want to be really far away, like you're at -1 or something. Then you're too far from where the limit is. You want to be very close. And then since x squared is continuous, you would just plug it in, and then you would get 1. Let's say, excuse me, if this function is not defined at 1, then what would you do? Well, you would do what you learned 2 sections ago, or last section, about how to find the limit if, so, let's say, it's indeterminate, or even some other way. You probably would use a graph or something, but you're trying to figure out what is going on at that x value. If the limit exists, then you write the number. If the limit does not exist, then this part does not have a limit. But anyways, I digress. Let's go ahead and look at the second one. So as x goes to 1 plus, or from the right hand side. Right hand side means numbers that's bigger than 1, so that means we're going to use this part. It tells us that the function is negative x plus 2. So then we're going to put 1 inside x of this function. So negative 1 plus 2, that is 1. So both sides are going to 1. So therefore, you want to say, because limit as x goes to 1 minus f of x equals to limit as x goes to 1 plus f of x, and then you can pretty much just make this conclusion. Or if you wanted to make it sound more like a sentence, because this is all equal to 1, limit as x goes to 1, f of x goes to 1. So if you want to write it like that, but this is kind of the complete proof. All right, let's try this. Actually, one more thing. Let me kind of show you how this graph looks like, so you're a little bit more convinced. So the split for this graph is at 1. So I'm gonna split this graph at 1. On the left hand side of this, it looks like a x squared. This is a x squared graph here, but there's a hole because it tells me that it's not equal to 1, so there's a hole. And then when it's greater than or equal to 1, it looks like negative x plus 2. Negative x plus 2 means there's a y-intercept at 2, and then the slope is negative 1. So technically, it should start here and then go down like this, but on the left-hand side of 1, it does not exist, so we would really only have a graph like this. And this one actually fills that hole because it is equal to x is defined at 1. So we can see that yes, both sides are going exactly to y equals 1. So our proof matches with the graph. All right, now let's look at the second example. Show that f of x equals to absolute value x over x. Let this function equal that. Show that the limit as x goes to 0 of f of x does not exist. All right, so let's just kind of think about it for now. If we put 0 in here, we get 0 over 0. That is an indeterminate form. That tells us maybe there's a limit, but we don't know. So we have to try something else to solve it. If we had one of those functions in section 1.3, we could have done something algebraic and find out what the limit is, but it's an absolute value, and we don't know anything that we can do to solve that. So what we're going to do is just do it analytically think about it. So to show whether a limit exists or not calculus way, you have to find the limit from the left hand side, and then you have to find the limit from the right hand side, and then we have to check what both sides are going to. So limit as x goes to 0 minus, that means a number smaller than 0. So something smaller than 0, but close to 0. So let's just say if we let x equal to negative 0.1. So that's close to 0, but slightly smaller than 0. So if we put that in the function, we get negative 0.1 over negative 0.1, but the numerator is in the absolute value, so we put negative 0.1 in absolute value. So absolute value of everything is always positive, so this is 0.1 over negative 0.1, which gives us negative 1. Okay, let's look at the second one. Limit as x goes to 0 positive, so we're coming from the positive side, so that is put a number in that's slightly bigger than 0 but positive. So 0.1 is a good choice. So the top is always positive, so we get a 0.1 over 0.1, which is 1. So both sides are actually going to different numbers, and so this one, the limit does not exist. So we want to say limit as x goes to 0 minus f of x does not equal limit as x goes to 0 plus f of x. Therefore, limit as x goes to 0 f of x does not exist. Okay, so this is, again, the complete statement you have to write. You cannot just show this and then assume the reader will infer your conclusion. You have to write a statement. So please be careful of that. Now, if you actually look at the graph actually looks something like this. So the right-hand side, as it approaches 0, it is 1. the left-hand side as it approaches 0 is always -1, and so they never have a limit at 0. All right, let's try this one. I think you guys are pretty good. So you need to prove whether this limit exists or not. And remember, the proof is the most important thing. And so to prove whether a limit exists at that point, you need to check the left-hand side and the right-hand side. So go ahead and pause the video and give this one a try. All right, so this is very similar to the previous problem. So we're going to check 4 from the negative side, and then we're going to check 4 from the positive side. From the negative side, we're going to use numbers smaller than 4. So that is 8 minus 2 times 4. And again, the reason I'm putting in 4 is because this is defined at 4. And so we can just put in 4. Like in the previous question where we had the absolute value x over x, it is not defined at 0. So if I put 0 in, it still gives me no no determinable information. So then we had to kind of go with a smaller number or a slightly bigger number. We would do this with this one. You can put in 3.9 if you want, but it is continuous at 4, so therefore we don't need to do that trick. Okay, so put that in, you get 0. All right, numbers slightly bigger than 4, we're going to use that second part of the piecewise. So then square root of 4 minus 4 is 0. So both sides are going to 0, then we can safely assume that the limit is at 0. So then the limit as x goes to 4 minus f of x equals limit as x goes to 4 plus f of x, and it's equal to 0. Therefore, limit as x goes to 4 f of x equal to 0. If you feel like writing this is a little bit cumbersome, you can actually skip that therefore, and then you can just write limit as x goes to 4 minus f of x equals limit as x goes to 4 plus f of x equals limit as x goes to 4 f of x equals 0. So this is, a pretty standard form. Like people understand if this is it, then this must equal, and they're all equal to 0. So this is very understandable in a kind of a probably the most concise way you can write to prove the limit.